And now I'd like to use this terrifying photo to talk about vorticles. We have this enormous, absolutely enormous explosion happening somewhere out in the Middle East. And what vorticles are little particles that exist within the plume. And the reason why you might want to add these particles is because it gives you this pyroclastic look. So all these little tiny bubbly details along the edges, you can push that further through vorticles. And the way it works is we basically have these vorticles affecting velocity, and we can push velocity in all directions. So I kind of picture this in my head as a hot piece of debris that's pushing velocity outwards in all directions. That'll create some of these bubble shapes around here. Additionally, as this moves through space, it also makes sense to have cold air pushing towards the plume as it moves outwards. So we want to find the zones that are moving quickly or that have the most pressure, and we want to push against that with this velocity, which kind of simulates cold air. And so if we have particles going in all directions outwards, and we also have velocity going against that plume, that's going to create these bubbly shapes around here. And that'll really help with that pyroclastic look. You can't really get this with disturbance. I mean, it helps a little bit, but disturbance will just make things fuzzy at a certain point. The look that you get from vorticles is more of a bubbly look. And what's cool is that you can oftentimes change the sizing of these little details just by affecting the p-scale of the vorticles. So it gives you a lot more control. Now, in practice, I don't always use vorticles because it's just another thing that you have to balance with everything else. And Pyro already has so many things going on. But again, assuming that you have time, assuming that you want to take the quality as far as possible, we should at least understand the basic workflow behind vorticles and what that can do for us. Before we get going on vorticles though, I want to talk about the resolution that this is all currently at right now. What you're seeing here is 0.05 on the voxel size with the adaptive substeps going up to 4. And so this is a pretty fine resolution for doing tests. And you never want to set up systems, or in this case, we're about to set up the vortical system, right? You never want to set it up with this really high resolution system because you'll spend forever just trying to put out test renders. Now, the tricky thing about that is this is what it looks like when we're at 0.1 with no substepping. It looks pretty bad, and it looks super blobby because things are moving fast. And just by comparison, that is supposed to turn into, wait for it, this. So we are kind of working blind here because this is completely different than what the 0.1 is doing. And this actually is a good thing to recognize as well, because so many times people are trying to use microsolvers and they're trying to pile on vorticles and all this stuff just to break up these smooth mushroom clouds, when the real issue is substepping and fast velocity. I mean, there you go. Most of our details coming from the substepping right here, and that already gets us the vast majority of the way to those fine details that we saw in the reference photo. But anyway, I just want to point this out. We are going to build this at a coarse resolution so that it doesn't take forever. Once it's working though, at the very end, once I'm happy with the system, I'll then switch back over and do a high-res simulation of this just to make sure that everything is sitting right. But again, this is a problem with the sparse solver. This is one reason why in production, I would probably recommend Axiom for most situations. However, it's good to just at least know these techniques. Anyway, that's enough talking. I think I've been jabbering far enough. Let's actually go ahead and do this. All right, well, the first thing that we need to think about is how are we going to get particles inside of dots? And there are, I think, a couple of ways of doing this. One way of doing this is we can take a SOP geometry right here. And this node is typically designed to bring in geometry from SOPs, but it's basically just like a container. And so, if we go to our smoke object, we have density, that's its own container for those voxel values. We have temperature, divergence, all of our fields, right? They just contain data. Well, it's the same thing here with the SOP geo. It's designed to import geo from SOPs, but the point is that it can hold polygons, it can hold points, it can hold SOP stuff. And so let's use a apply data to apply that to our smoke object. So if we go here, let's also go down to the bottom and change this data name to interior particles. Let's also copy that. As soon as we have interior particles, that's being applied to our smoke object. Now, if we go to our geo spreadsheets, under the smoke object, we've now added our, where is it? Interior particles down here. So now we can fill this with some particles. Question is, how are we going to do that? Well, we also have this thing that we can use called a SOP solver. And that SOP solver right here will allow us to access SOP nodes and then adjust the simulation data so that we can throw it over to the interior particles. So just to re-emphasize that, we have our SOP solver. That's going to generate the points, which we then throw into the SOP geo container. Let's check that out in the next video.